This is a surprisingly good turnout for the last session of the day on a Thursday. This, in fact, is the latest I've ever been here in about 10 years. So I hope everyone's not as sleepy as I am. I know when I get sleepy too, sometimes my words don't come out right. So I've asked Dr. Vibha here to give me really short and easy words to say. I'm sure everyone's, had a long week, and we're going to be talking about some really cool science about battery recycling, battery refurbishing, re-energizing batteries. And I kind of think of this advanced science as almost magical, and I think it's great that we're here in Las Vegas, because I think I'm going to treat everyone to a magic trick while we're here. And someone in this audience is going to be so happy because I'm going to double their battery capacity on their phone right here. So one of the worst things to do is audience participation, but I apologize. I really need to do this to make this work. So if we could get our phones out, please. And I don't know, I guess stand up if you could. Maybe that'll make it a little bit easier for this magic trick. So the first part of this magic trick, I've got to separate it out by phone type. So unfortunately, or fortunately, if you have an iPhone, keep standing. If you have anything else, sit down. Now, it's odd that I asked that. It's just, when you're judging battery health and capacity, really iPhone is the only one that shows your percentage of health. So sorry, Android users or, Samsung users, but, in their defense, I don't think there's ever been a Samsung battery issue in their mobile phone history. Okay, so now with your iPhone, take a look, go right into settings, okay? So settings, and scroll down just a little bit and click that battery section. Do you see that where it says battery? Okay, all right. So from there, click on battery, and then you're going to scroll down where it says battery health. It might say excellent, good, poor, whatever. Click on that, because up from there, it's going to show a percentage. So hopefully now you are seeing a percentage. Now, if you have 100%, good for you. You've got a new phone. Sit down. Okay. 95% and over, sit down. All right. 90% and over, sit down. Wow. 85% and over, sit down. 80% and over, sit down. Wow. Okay, so we have enough people. So let's ask what we got. What do you have? 73, 78, 79, 77. We've got a winner. So you're going to be our lucky participant. What? You can't. You have a Samsung. And I just said no one's ever had any issues with any Samsung batteries. Actually, we had a collection event this past weekend. We got a Samsung Galaxy Note 7. I ran away from it scared. So 73%. The funny thing with Apple iPhones too is that anything under 80%, they actually will throttle your performance to make sure that your battery, or that basically the health of your phone works and you don't get random shutoffs. So anything under 80% is, can be rough. So imagine as a recycler or as a consumer one day just walking into the store and saying, hey, my battery is bad. Can you replace it? Do I get a new phone? What if it's like taking your dog to the vet and getting a shot? What if we can just magically increase the capacity again through re-energizing, refurbishing your battery? That's what we're going to be talking about. One of the topics we're going to be talking about. But now for your magic trick, I want you to come up because I'm going to right here and right now double your battery capacity. You see all these tools that I have up here? Okay. Here you go. It's a battery charger. Yeah. Now, I didn't say how I was going to do it, but I did it. It's because I like to deliver on my promises. Now, you're welcome. That's actually made from recycled plastic. Not recycled battery, but recycled plastic as well. And I didn't expense it on King. I actually bought it myself. Okay. So, think about that, though, in the future, is actually being able to, repair these batteries, re-energize them. And that's why we're here today. And I want to introduce Dr. Vibha Kalra, who is the brains behind the entire operation. We're very excited to present this to you.
Okay. I have to say, this is the nicest introduction I've ever received for any of the talks I've given. Never been termed a magician, and I have a big standard to live up to now, so I'm nervous, but I'll jump right in. So thank you, Phil. All right, so let me start this with this very high-level introduction where I'm sure, hopefully, many of you will agree that one of the biggest technological breakthroughs that has happened in the past decade and a half has been when Nissan launched its first mass-produced electric vehicle back in 2011, the Nissan Leaf, right? And since then, as we know, there's been no looking back. And this is nothing but an engineering marvel, right? On the left, you see this image from a Tesla Model S battery pack, which, as many of you would know, is composed of 8,000 of these Panasonic cells integrated together in this beautiful way to enable the 300 to 400 mile range that we know of today. Right. And the good news is that, or not so, good news is that despite the tariffs and the EV market is looking pretty strong, it's still expected to grow to the levels that we see here by 2040. Now, all this is great, right? But one of the big serious challenges that this field has been sort of neglecting for the last many decades of development, as we are now very aware of, is right here, right? We all understand the very serious supply chain challenges, and United States is in a particularly vulnerable position with 90% of battery raw materials that are being obtained from foreign suppliers. Of course, there is a lot of pollution and environmental challenges associated with mining itself. And then all this, and if we think about the end of life, we are generating tons and tons of battery waste, and a lot of it is ending up in landfills, which is causing all kinds of land, water, and soil pollution. Right? So a very simple question that comes to, a very obvious question that comes to mind is, can we not recycle this battery waste to generate a domestic supply of critical minerals? Of course, the answer is not that simple. The economics and the environmental impact of these processes are not in our favor right now. The recycling processes come with a large energy consumption, a lot of water usage, a lot of CO2 emissions. So then a modified or a revised question is, can we recycle this battery waste in one economically viable way and also environmentally friendly way, which is more feasible and sustainable to generate a domestic supply of critical minerals? All right. So before I get into some of the R&D and technologies we've been working on in our lab at Cornell University, let me give this away to Phil to talk a little bit about the current recycling processes in the industry. Phil, it's all yours.
So our current recycling process is really, we're processing a lot of consumer electronics, a lot of other types of electronics. And what we do is we have got to pull the batteries out first, dismantle, and we shred everything without the batteries. Batteries go downstream to a battery recycling company.
Wait a second. So the video is playing. Is that okay?
We can go on right to the next. So what happens? These any battery recyclers here that make black mass? No? Okay. Yeah, there's not too many of them, but any electronics recyclers here? Okay. I know exactly what you do with your batteries, so they go downstream, and our partners will make a black mass that will then go to another process. So I want to go to the next slide here. We've got, a couple different processes for creating, compounds and elements, for reuse. But, I know you promised not to give me any too difficult of words to pronounce, but, we've got two main ways to do it, right? Through a pyrometallurgical process and a hydrometallurgical process. Now, on the pyro side, right, it's very energy intensive. And it definitely is a high cost. And the same thing through the hydrometallurgical process as well. A lot of harsh chemicals, still kind of expensive. So our goal here is to, through reuse and through refurbishing, cut out all that intensive energy. And also on the recycling side to shorten that, recycling loop as well.
Okay, great. Thank you, Phil. So, so sorry that the video didn't play, but as Phil mentioned, currently the recycling process is a very brute force method where you take all this waste and put it in a shredder, which I know you didn't see in the video yet, but you put it all in the shredder and create this powdered or a slightly processed powdered waste, which is this black powder that we saw in this picture right here. And then you have to redo the whole process of recovering the critical elements, refining them, cleaning them, and then resynthesizing all of the battery electrode materials, and then redoing the whole process of manufacturing. So a very large circularity loop is what I would call that. So what is our solution? We want to create solutions which are not one size fits all, right? Because as we saw in the exercise that Phil had you all do, we have a range of state of health of batteries at the end of life or at midlife, and not all of them need to be subjected to this brute force of shredding and redoing the whole thing. So what our solution is, that for mild and moderate state of health batteries, we can do a direct repair or regenerate the batteries. And of course, there'll always be batteries that are way more degraded and would still require the long loop. But there is a huge fraction of batteries that we can deal with without having to do this long circularity loop. Now, for that repair method, again, the vision that the ultimate vision that Phil talked about is, imagine you have a laptop with a battery at 60 to 80% SOH. You take it to an Apple store and they just repair your battery and you're back to as good as new. Of course, to enable that vision, there's a lot of steps that we need to enable. We have demonstrated the proof of concept in our lab, and there's some exciting work that I'm looking forward to sharing with you. All right. So for this repair and regeneration is what we call it. We have developed a direct electrode to electrode regeneration method where what we have shown is that you have a battery with a mild to moderate with a mild to moderate degradation or a reasonable SOH at end of life. We open up the spent battery. We use a recycling solution. So it's almost like cleaning out your coffee machine. So we use a solution to repair the blocking layers that are produced at the electrode electrolyte interfaces. And then while the electrodes are still attached to the current collectors, they're still in the same form factor as they originally were. And then we just assemble the battery back, right? So there's no shredding, no redoing the whole process. And of course, a big part of it is investigating how the battery got degraded in the first place, and essentially reversing that degradation is what we have shown. So this is, let me just jump to the capacity data that we have obtained with our recycling method or regeneration method to be more precise. So on the black, so this is basically how much is the capacity, or in other words, how much charge is stored in the battery, which is directly proportional to the runtime of your battery in a single charge. And then on the x-axis, you see the cycle numbers, how many cycles the battery is running, charge and discharge. Now the black curve is a pristine cell, which, as you can see, goes from almost 100% SOH to 80% SOH. Once it's at 80% SOH, we give it the regeneration method that I mentioned about, and then it goes straight from 80% to 95% of pristine value. And in fact, these recycled cells run even longer than the pristine cells. We have our reasons to believe that because in the recycling process, we are able to retain some of the good things that happened in the first cycling or in the first life, which are enabling it to last even longer. Of course, I'm happy to go into the details of chemistries and the exact reasons we have, but for now, for the sake of time, I'll leave it at that, but I'm happy to answer detailed questions. And then, in fact, we have demonstrated that these first recycled batteries, when they reach end of life at 80% SOH, we can again recycle them to a second or a third life for the battery. Now, how do we enable this method? Of course, this is almost the sort of the final outcome of what we have achieved. But of course, a lot of investigation of the degradation mechanisms has happened, has been a part of being able to develop a process like that. In addition, in our lab at Cornell, we have a whole suite of tools developed to do real-time monitoring of these processes. So we can look at the inside of the process or inside a battery and see what kind of changes are happening inside the battery as they are running, and also as they are cycling, and also as they are being regenerated in our processes. So this is actually direct monitoring or tracking of the chemistries that are evolving as we regenerate our battery, and how the blocking layer, which is formed over hundreds of cycling our cells, that is formed at the electrode electrolyte interface, how that blocking layer is being gradually dissolved out in our recycling or regeneration process. So we can monitor that in real time. We can also monitor how our regeneration process is helping improve the impedances and resistances inside the battery. So this is a great tool that allows us to develop these kinds of processes. We can also go down to even smaller scales, because a lot of these blocking layers that I'm talking about, which are called solid electrolyte interfaces or SEIs, they are they are nanoscale sizes, right? And we can also track the actual morphology or the structure of these blocking layers. So as you can see on the left is a pristine cathode. In the middle is a degraded cathode after its end of life. And you can see this blocking layer, which is very thin, but it blocks the transport and impacts the performance directly. And then on the right, you see after we have done the regeneration, how this blocking layer is removed. And that is then reflected directly at the capacity jump that I showed you earlier. And then this is also a similar study, but on the anode side. So we are also simultaneously regenerating the anode and cathode in the same regeneration process. All right. So then, of course, to demonstrate how this process is helping and leapfrogging, we did detailed life cycle and techno-economic analysis, where we essentially compared our process to the hydrometallurgy and pyrometallurgy process that Phil talked about, which is the state of the art right now in the industry. And this is just a flow chart of all the steps of each of those processes. Of course, for pyro and hydro, the circularity loop is much longer, right? You have to start with shredding the whole thing, crushing them, and then starting to do the separations and refining and resynthesis of the cathode and anode materials, and then putting them in the battery. While in the direct electrode to electrode regeneration process, which is at the bottom, we have much smaller number of steps. So this is sort of the outcome of this analysis of life cycle and economics. And we can see that our process can generate 3 times higher revenue at scale and 50% lower cost compared to hydro and pyro metallurgical processes. And this cost savings are, as you can see on the curve on the right, these cost savings are directly coming from, a big chunk of it is coming from having to eliminate cathode production and many of these other steps that I mentioned about. And this is in addition to creating a lot of economic and environmental advantages by eliminating those processes. Another perspective to think about is that at this, in the current state, domestically, we don't have much refining and extraction and even cathode synthesis capability in-house in the United States. And if we are able to eliminate those processes, this process becomes a lot more compatible with the current available technology and processing available in the US. All right, so this essentially what we have shown you is this blue. If you can see the blue circle, we have shortened the loop by being able to directly regenerate or repair these batteries at end of life. All right. Now the question comes, what if the battery is too degraded to be regenerated? Yes, we are very aware of that. There will be batteries which are much lower SOH at end of life and will require a longer loop recycling. So we have developed a process in our lab where we go through the whole circularity loop of shredding and then ultimately processing, and we have developed a closed loop process. But in this one, what we have shown is that we can use organic acids which are not toxic, unlike the toxic sulfuric acid used in the industry today. So we've shown a closed loop process using very mild organic acids. So and bioacids in particular. So this particular project is in direct collaboration with our very valued partner, Phil from Sunnking, and another professor at Cornell in the biological engineering department who's a synthetic biologist, Buzz Barstow.
If I could answer one question you're probably thinking, yes, that is the best picture we could find of me.
Yeah, so that's why we gave you a choice to provide whatever you wanted. All right. So, like I said, we have created a closed loop recovery method starting from real black mass, which thanks to Phil, we were able to get in-house from personal electronics. And we have eliminated the need of harsh toxic acids, sulfuric acid in particular, which is used in the industry today. All right. So, in a nutshell, this is a process. It's a circular process. We start with a black mass, which is supplied by Sunnking to us, which has, I know it's called black mass. The color is, it has a large fraction of graphite from the battery anodes, and that's why it's black. I like to call it black mess because it's just everything. It's just everything has been shredded. And when you're thinking about personal electronics, the mess is even worse because there is the volume, the range of chemistries that are in today's personal electronics is extremely wide, even though we give it a common term of lithium-ion batteries, but within the lithium-ion batteries, there's a wide range of chemistries that we work with today, right? And when you mix these volumes and volumes of personal electronics and their batteries and spread them all together, what you end up with is practically no control on what you have with you and the range of compositions that you achieve. Unlike an EV battery, which is sometimes more controlled. It's still very messy, but a little more control than the personal electronic black masses. So this black mass, in addition to graphite, which is the anode one, but from the metals, it has everything: lithium, nickel, cobalt, manganese, copper, iron, aluminum, you name it, and we have a lot of these. And so what we do is we start with the first upstream extraction process, which is using a bioacid or an organic acid, which is generated microbially. So the particular acid is gluconic acid, which is way milder and sustainable than sulfuric acid is, less toxic. This acid is also available commercially, and in fact, the commercial organic acid, gluconic acid, is also produced microbially, which I'm not sure many people may not know. So we use that organic acid, which allows us to extract out all the metals. So it leaves out the graphite. It's not selective toward metals, but it extracts out all the metals, which is listed right here. And then at that point, we have the big task of refining this, because any impurities, in the battery electrode materials, is going to very severely impact your battery performances. So then what we do is we do a combination of electrochemical refining to remove out. So instead of extracting individual metals that are important to us, we remove out the impurities instead. So this saves us time and money. And we remove out the impurities, particularly copper and aluminum, which are coming from the current collectors in the battery, but are not needed, and in fact would severely impact the performance in battery electrodes. We do the electrorefining, we do the co-precipitation, we do the resynthesis of the NMC cathodes, which are, and then also do the upcycling to make sure that we are getting NMC 622 or 811. And then we create cathodes and then put them back in the battery. And what I have here is our final results. Of course, there's a lot of experiments that have gone into developing this method, but I just wanted to show you what we achieve at the end. What we achieve is the NMC 622 is right here, which is produced from, remember, personal electronic battery, which is very cobalt heavy. We are able to achieve the exact same NMC structure as pristine, and in fact achieve battery cycling performances which match the pristine materials right here. All right, so just to do a quick wrap up of what I just presented, we are in a very vulnerable position in terms of supply chain, and it is critical that we come up with creative solutions that can allow us to regenerate and recycle our batteries in the most economical and environmentally possible way. And for that, we have shown two technologies or methods. One is, which is a direct electrode to electrode regeneration, and highlighted in the blue circle, which is the aim is to shorten the loop for this large fraction of batteries that are at reasonable state of health at the end of life. And then on the right, we have shown an extraction-based, shedding an extraction-based process using a friendlier and less toxic and more sustainable acid leaching-based methods, which and we have fully closed the loop by putting them in new batteries. All right, with that,
What I find most exciting about this as an iTAD provider is just the sheer amount of mobile and laptops that we test and refurbish. So instead of, searching for parts harvesting, we get a lot of laptops that are great, but they just don't pass the battery test. So instead of going out and maybe purchasing replacement batteries to be able to re-energize those, is a big deal. Not only could it be a time saver, but it could be just immense savings. I think maybe I'm going to ask about, if anyone wants to get involved, how to get involved. But maybe first we ask some questions. And I'd like to start one because as battery chemistry changes over time, right? There's always new battery breakthroughs, and we're seeing a lot more LFPs, right? Lithium iron phosphates, especially in the storage or automotive industry. Talk about your work with LFPs and how that could be possibly, similar to the NMCs.
all right, great. Thanks, Phil, for that question. So absolutely, LFP, all the numbers tell us that LFP market is growing very fast. Because of the lower cost. And so let me start with this. So there are two parts to it. One is our method is simply investigating what the degradation mechanisms are and then reversing them, right? And the degradation mechanisms, largely speaking, are similar in many of these battery chemistries, right? There is this blocking layer, there's lithium loss, there is cracking of, there is loss of the active material. There are nuances that can cause variations from one chemistry to the other. So from our standpoint, with LFP also, we could do the exact same method. It's more of an optimization, investigating what are the key mechanisms that are playing an active role in the early loss of SOH and then in the moderate loss of SOH and then reversing that. And in fact, we do have an active project in our lab where we are investigating LFP chemistries and we believe the similar methods would be applicable to LFP as well. So that's from the technology standpoint. The other aspect is that, and this technique, we do believe, would actually be even more attractive for LFP, right? In batteries such as LFP, where the cost is low, the economic value of recycling is harder to achieve. A shorter loop recycling would make a lot more sense in a battery chemistry such as LFP. And another point that I wanted to make, which is now turning the tables back to NMC, is in one of our conversations with a large OEM company, I won't name them, what we are hearing is that with the increase of LFP batteries, the demand for recycling high SOH NMC batteries has gone up even more. That's because up until some years ago, when LFP was not as high in production, a lot of the 80% SOH NMC would be taken over by stationary storage companies. But now with LFP coming in, they have an alternative, which is of a new battery, which is probably as much cost. and as a 80% NMC battery. So the demand for recycling NMC batteries at that level of SOH has gone up a lot, and a process such as this could really be a paradigm shift.
Okay, one more question for me. What's the biggest obstacle right now for something like this? Is it capacity, reuse markets, safety, policy?
So I would say this is the way I would describe this is that we have done a robust early stage demonstration and proof of concept in a lab, right? There is a lot of work to be done, right, beyond this. And this is something which I would say we cannot do it alone, right? So the key thing to take it forward is there's a lot of pieces that need to come together. This could be paradigm shifting technology. We need Sunnking and Phil have been really kind and gracious to be part of our journey, but we need a lot of partners, right? We need partners who will who have electronics recycling. Then we need partners for disassembling of these devices, which we already have. By the way, we are already in the process of some of these partnerships to take this forward, but we are looking for more at all times. We will need to go into the steps of disassembling real batteries, and then a larger scale batteries rather. I mean, these were real batteries too, but larger scale batteries, and then regenerating them, and then putting them into larger. So scale up would be one piece. So we will definitely need a lot of industrial engagement there. From the safety standpoint, I think there is a lot of the industry is moving forward at a very fast speed in that direction as well. So definitely we can leverage a lot of those learnings from the safety standpoint as well. But clearly, if we can continue to show at higher scales the economic value of this process and the shorter loop, I feel the path can be progressed fairly well.
Great, thank you. Let's get some questions out here, Mr. Adam Shine.
I don't know. Is this on? Can you guys hear me? Okay. First of all, fascinating presentation. Thank you for the work that you're doing. Obviously, batteries are a major concern and a major topic amongst everybody that's here, especially us in recycling, but also ferrous guys, MRFs. Everybody really sees these come into their stream. In our case, we're prepared for them, which is good. But I guess I have some questions around, A, how safe is your method? Because battery fires are a major concern. So is it safe? And while it's obviously on the front edge, how easy will this be to scale, and how far out do you think it is from being commercially available?
Okay, great question. So let me start with the safety aspect that you asked. So to me, the safety aspect is something that needs to be addressed at the upstream side of it, which is where you would discharge the battery and disassemble it, right? Once it is disassembled, then we are really working with the materials, which we are working with, standard solvents to regenerate them, right? So that upstream piece of disassembly, we want to leverage developments in the industry, right? We don't want to and then attach our regeneration process into that disassembled cell. So once it's disassembled, it's very straightforward from the safety standpoint. And in fact, we do have a partner currently who we will be starting to work with, who can disassemble, who do this level of disassemblies in their facility. And in fact, right now the process is manual. Having said that, there's also a lot of work going on, I'm sure a lot of you are familiar, there's to do robotic disassembly. So there's definitely a lot of scope and opportunity in developing robotic disassemblies where we can work with those partners who are doing manual disassemblies and then create more robotic methods to do it. there is opportunity for development on that side. There's also a lot of opportunity for research, right? Cornell has a strong robotics team, with professor expertise, very strong robotics. There's soft robotics that is, with very high dexterities, which could really be extremely enabling for technologies like this. And that's moving forward, irregardless of our method, right? So we can leverage a lot of that development into our techniques.
I'd like to steer the conversation a little bit into absolutely useless. I was wondering what your thoughts were on the SD12 speaking.
Loud enough as it was. Did you catch that, or do you want me to repeat it?
We did, yes. Actually, we're talking about that pretty soon. I think we have a possible expert on that right there. You wanna? I don't know if you have anything to add on that. Oh,
Wondering what you thought regarding SB 1215. You think it'll make a difference?
Tough to say at this point. We're going to have some further discussions about it. So one thing I would recommend is that if you're involved in ReMA, we do have a monthly call and we talk about a lot of these bills. You should join those because if you're a ReMA member, if you're not, I suggest you become one. But we talk a lot about these various bills with regards to batteries and other legislation that affects the e-scrap business. So I don't really have any major thoughts on it right now, but we can talk maybe after.
and then we do have, right, we're actually discussing it through ReMA later today as well. Any other questions, statements about batteries even? You have a battery, anything? All right.
Hey, Mike, how quick is the DEER process, the DEER? Is that something that I could walk into an Apple store and leave 20 minutes later? What about with a propulsion battery if it's scaled up to that size?
So as of now, it takes several hours, not at the rate of 20 minutes. Having said that, the vision is to sort of go into optimizations and see how we can make it faster. But having said that, the way I envision it, if it were possible, when which we strongly believe that when we get to this deployment level where we can just walk into a Apple store and get it repaired, even if it takes a day, I think this could be very valuable. Where you submit you take your battery and then collect it the day after. So to me, we're not as focused on the length as much as we are on the fact that we are directly regenerating it.
And then, I guess related to that, how much variance is there on applicability of DEER when you're talking about a sort of 80% sort of SOH? Like how much variance is there on a battery per battery basis?
Great question. So that's where this, as of now, at the lab level, we are able to handle. It's very repeatable, and we are able to handle a range of batteries and samples. Having said that, yes, the variance could go up when you're talking about batteries used in real life, but having that said, the mechanisms of degradation are still largely can be categorized into a few different umbrellas, right? And if you're directly tackling those mechanisms and addition of some of those mechanisms, then we should be able to handle a wide range of degraded batteries. Because we are essentially removing the blocking layer. So yes, there may be some variations in how the blocking layer is from one battery to the other, but if we are removing most of it, we may be able to just handle those variabilities. But yes, this would be a step forward in looking at a wide range of end-of-life batteries with different usage histories to further validate this process.
Hi, over here. Thanks for your work. I was surprised on your slide to see the low labor cost in your TEA. Did the TEA include the labor for disassembly? And connected to that, can you talk about whether redesign or standardization in batteries would be necessary, do you think, to have a commercialization for this process?
Yes, good question. So yes, we did include the labor and cost of the disassembly in the TEA and LCA analysis. As of now, there are companies, for example, Princeton New Energy, who actually does the cell level disassemblies. They do it manually. So in this current, with the current state of the art batteries, EV batteries is what they're using. So it is possible. But having said that, design for circularity is obviously a huge, topic that people are interested in. And a simpler design could definitely make it, would be a great enabler as well. And would make that disassembly process much easier. But having said that, even in the current state of the art, EV batteries, it is possible to disassemble.
I think too with ReMA's championing of the right to repair and the EU regulations that are coming out, it's been much easier to have a battery that's in good physical condition that would be ripe for this process. Hasn't always been the case, but even Apple that has maybe been a little less friendly to right to repair. I know their new MacBook Neo came out, right? And they gave it probably their highest repairability score in a long time. And I believe they stopped using the glues in there. And I think, electronics will be coming a little bit, better for our industry, which is great, which means we'll get, better, batteries to work with and that we can use in this process.
Thank you. Effective. Okay. I have a question about just like person like myself, if we want to go in a battery recycling business, what is the just approximate cost difference of the process to process, like say pyro versus hydro versus direct or DARE? What's the relationship of operating cost? Processing cost.
Yeah. Thanks for the question. I don't think I would have specific numbers for you off the top of my head. I don't know if Phil has any values to share. But having said that, if you look at our TA analysis, this is, I don't recall the exact numbers, but I think we have the percentages, which let me listed right here. So this is, so these are sort of the comparisons in terms of cost of recycling. So you have the dollars per kilogram of feed, and compared to the hydro and pyro, the DARE revenue can be very large compared to pyro and hydro, largely because we are really shortening the loop. So the number of processes that we are subjecting our materials to is much less. So you're saving a lot there. And similarly, from the cost standpoint, as we can see here, the biggest savings are from shortening the process.
Can you talk to us a little about the commercial reality of it, where you're at with it in the process before it becomes commercial? And where do you expect that to be done? Can it be done like at an Apple store, or are you thinking it's going to be done at a separate facility off-site?
Sorry, I'm not sure if I fully get the question or I heard the full question, but are you talking about,
So is the technology available now on a commercial level?
No, so currently the technology has been demonstrated at the lab level. So we have a proof of concept, and at this time it is ready to be tested at larger scale with larger scale batteries and validate it there. But we do have a very clear pathway from these companies that are doing the disassemblies, and we can obtain the disassembled electrodes from them, which we can then process to make larger scale batteries.
And the timing of that? Timing to become commercial from your lab scale?
Timing. So, I mean, at this stage it can be, so as I mentioned, I think we need a lot of industry engagement, which we've done some successful engagements and stakeholder partnerships at this stage. The years could be variable from 5 to 10 or sooner if we have more support. Policy can play a role there as well, right? So the more support, we can do it faster. So really what the call to action for us is here, if any of you have interest in what we talked about and are interested in discussing or partnering or even exploring synergies, we would love to hear from you.
Yeah, that brings up the last side. I was going to ask, if you're interested, how do we get involved? How do we move this along?
Do you want to? So yes, so we cannot do this alone.
So we're looking for anybody in the industry really that touches batteries. So if that's something that you're interested in, please reach out to us. We've got Vibha's contact information right there. We really think that this is something in the future that could provide immense dividends for us, especially on the regeneration side. Before we wrap up, does anyone have any questions maybe regarding participation on this or anything else about batteries, regeneration, anything? Oh, all the way in the back.
I have a technical question when it comes to shredding and then fires. So I seen from life cycle and redwood materials and all the companies recycling batteries. It's the best way to do it without absence of oxygen, liquid, to prevent explosion and fires. Or what do you think the future of shredding batteries is going to look like?
That's
a tough one.
Yeah.
I am right with you on that, and I think it's literally just the absence of oxygen too. I would like to see, on the industry level, for more electronics recyclers to be able to do that and not just spread it amongst battery recyclers. Kind of make the equipment more accessible, right? If you can do that at a level at your facility too, it certainly, for me, seems like it would be safer than just storing them and shipping them out. But
Yeah, on the island, and I want to take those things out. It's if it's swollen, or if it's swollen, we can ship it out. So, my idea is to get it to black mass. But, is there a process? I mean, I'm afraid to do it because I don't know how to do it. But is it pretty easy to do to deactivate the black mass and just send out the black mass itself, or just neutralize it? I don't know if I'm.
no, you explained that nicely. Not really, not for us. It's quite difficult. The equipment is, very expensive. It takes up, a decent footprint. So there's definitely a barrier to entry there. So, if it's on a smaller scale for you, you've got to take those precautions with, any type of the remediation tool at your disposal, like cell block or the fireproof wrapping paper or something like that. So but hopefully as we grow as an industry, it becomes more ubiquitous and more accessible to have that kind of equipment and to make it cheaper, less expensive, because I think it'll just make the industry much stronger, much more safe, and we'll probably see a heck of a lot less news articles about facilities burning down.
If you're in the U.S. and you're doing that, I would reach out to your state environmental agency for any requirements that they may have for that kind of treatment of hazardous waste in U.S. territories or states.
And make sure that you're following any type of regulations, DOT regulations. And I know on the e-commerce side too, they've become a lot more strict with shipping batteries. So it's always so important to be aware of any type of regulations there. You're absolutely right. Any more questions? This goes to 12:30, right? 12:30. So we actually timed that pretty well. I can't believe everyone here stuck it out the whole time too. Hopefully you got like a late checkout so you can get a nap in before you go. But we greatly appreciate you coming to this last session, and we appreciate the support, and we really look forward to hopefully hearing from some of you. And heck, maybe a few years from now we'll come back and we'll talk about how this is in process, and I don't know how rich it made all of us. Any last words?
No, thank you so much. I echo Phil's thoughts. Thank you for staying until the last session. And we really, really look forward to hearing from you and doing some wonderful collaborations and partnerships together.